We are operating strictly within the confines of the twisted boundary grid WBA operator, analyzing its behavior on a finite Ulam mesh. Every data point we examine here is strictly scoped to two specific grid resolutions, n equals 8,192 and n equals 16,384. Across this grid, we are evaluating a macroscopic parameter band. We are varying the parameter epsilon from 0.70 to 0.74, stepping forward in increments of precisely 0.01. Previous scans in this numerical regime established a baseline. The entropic spray originally observed in the B2 band collapses, localizing the system's mass into a single-cell spike. The central inquiry of paper 53 asks whether the chaotic geometry lurking beneath this leading spike smooths out over a broad parameter sweep, or if our standard numerical sampling intervals hide the volatility. Distinguishing actual structural stability from illusions created by finite grid sampling is a necessary step to evaluate Ulam discretizations accurately. Let's examine the leading eigenvector, V1, at this macroscopic scale. Across 0.01 increments of the coarse-band, this leading state acts as a sharpened null. It remains static, resisting any geometric variation. The cumulative mass widths, K50, K75, and K90, are identically equal to 1. All measurable vector mass is locked inside a single column. The top 1% mass fraction is exactly 1.000000 for every combination of epsilon and n tested on this band. The invariant density proxy does not stretch, diffuse, or shift in response to the changing epsilon parameter. In parameterized dynamical systems, shifting a core variable typically induces some measurable continuous deformation in the leading state. Here, we observe absolute rigidity. This invariant density proxy constructs a frozen surface geometry. Looking strictly at this top layer, the discretized system projects an illusion of stability. Beneath that frozen leading state, the subdominant spectrum, the second eigenpair, λ2 and V2, operates as a chaotic undercurrent. Spatially, V2 forms an ultra-high-frequency Wavepacket. It is highly compressed and physically anchored near the exact same leading center spike. If we measure its absolute mass, the concentration is extreme. At the 16,384 grid resolution, the K90 absolute mass metric condenses down to just 2 grid cells. But the absolute magnitude masks the internal mechanics of the vector. To see the actual structure, we have to look at the raw, signed geometry. Within those 2 concentrated cells, the vector oscillates aggressively between positive and negative values. At the 16,384 resolution, we record roughly 3,800 distinct sign changes confined inside this localized space. This count scales almost linearly as we increase the grid size n. This confirms we are observing a high-frequency grid phenomenon rather than a stable physical feature. The subdominant spectrum operates independently of the frozen surface. It functions as a structurally fragile dark matter mode, densely packed with high-frequency, localized oscillation. To evaluate how this chaotic geometry reacts to the parameter space, we map the finite-grid gap proxy across the different values of epsilon. Standard practice in numerical dynamics is to scan these parameters using macroscopic steps, commonly an interval of 0.01. This chart maps the gap proxy across epsilon. Using 0.01 coarse-band increments, it traces a stable, interpolatable trend between 0.70 and 0.71. These wide gaps suggest predictability, implying a smooth mathematical progression. Paper 52 introduced a critical intervention, probing the interstitial spaces between these points at a much finer resolution of 10 to the minus 3. Plotting the microband data shatters that illusion. Trapped between the coarse points, the gap proxy undergoes violent, non-monotone vertical excursions. While the adjacent coarse points show moderate variation, the interstitial space is volatile and structurally unstable. This is a Nyquist-style aliasing trap affecting our finite-grid spectral diagnostics. The 0.01 sampling interval is physically too slow to capture the high-frequency structural variations occurring within the subdominant matrix. Coarse parameter scanning does not average out the underlying spectral chaos. It masks the severe finite grid instability, generating a deceptive aliasing artifact. These findings map the internal structure of the Ulam discretization on this finite grid. We are left with a dual-layered reality. An inert invariant density proxy sits directly above a parameter-sensitive, structurally fragile subdominant spectrum. This split behavior directly challenges the finite grid smoothness folklore prevalent within transfer operator theory. There is a common expectation that established bounded variation estimates and a certified spectral gap will naturally yield smooth parameter dependence for these eigenpairs across standard grids. The data gathered across this coarse-band scan proves that expectation incorrect for this specific finite implementation. Macro-level mathematical guarantees do not automatically force smooth geometric behavior in the subdominant Ulam vectors. Assuming parameter smoothness based exclusively on coarse finite-grid sampling is an analytical vulnerability. To ensure these results are applied correctly, we must enforce strict operational guardrails around the scope of the data. Every pathological behavior detailed here is a structural property of the WBA Ulam matrix, strictly bound to the finite grid resolutions of n equals 8192 and 16384. We are not observing a thermodynamic phase transition in the underlying dynamical system. The severe, chaotic oscillation of the second eigenvector provides zero evidence for a loss of bounded variation regularity in the true continuum invariant density. The gap proxy metric itself must be understood entirely as a discrete numerical artifact. This finite grid proxy does not bound, touch, or violate the certified continuum spectral gap lower bound of 0.6509 established in paper 37. The rigorous continuum mathematics remain untouched. The Ulam discretization operates through decoupled numerical realities, demanding rigorous sampling hygiene when interpreting this subdominant dark matter.